Chapter 17, we're going to get started on what's called classic algebra problems. And we're going to start out talking about specifically mixture problems. Okay, the formula that we're going to apply to these problems is the number times the price equals the value. So, for instance, in a situation where 10 apples are bought at a price of 23 cents per apple, what is the value of all 10 apples? Okay, well, 10 represents the number of apples bought. 23 cents represents the price of each apple, and if we multiply the number times the price, we have 10 times 23 cents, and for the value we get $2.30. Okay, so this is just a straightforward application of the formula, but these aren't the classic algebra problems that we're talking about or that we're going to be solving. These classic algebra problems involve the application of this formula twice. So for instance, we have a number of apples and oranges that are bought at different prices and a different number of each, and then each one of them would have their own value, and so we could add those together to get a total value. Okay, so what's going to happen is there's going to be some missing information. We're not going to be told the number and the price of the apples and oranges. Okay, and that's just to give you an idea as to what kind of problems we're going to be looking at. So here are the steps. Our first step is to take the table, and we're going to use a table to organize the information in the problem. And we're going to fill out two columns, the number and price column. One of them will have to use a variable to complete, and so once we get the two columns completed, we multiply them together to get the value column. And so at this point, we're just going to have expressions and not necessarily actual single numbers for each value. Okay, and then we're usually given some information about the total value, and so we combine the column with the unused information from the problem, and we write an equation. Okay, so enough beating around the bush. We'll get down here and get our hands dirty. Alright, so these first few examples, we talked about various equations in the previous chapters. Okay, what we're going to do with these first few examples is just simply complete the table and construct the correct equation, and I'll leave it up to you to finish the equation and solve for the variable, which you should be able to do. So example 1 reads, Don's coffee shop makes a gourmet blend of two types of coffee. Coffee A costs $5.40 per pound and coffee B costs $3.20 per pound. If you were to order 5 pounds of the blend for a total cost, and don't just read over that word total, it's important, $19.30, how much of each type coffee does Don use? So as I stated previously, this is incomplete information. We don't have all of the numbers. We do have the price of each, price per pound, and so this information can go directly in the price column for coffee A and coffee B. So what do we have for A? We have $5.40, and then 320 for coffee B. Alright, so number of pounds. Where in the problem did we mention the number of pounds of coffee A or B? Well, the only place where pounds comes up is here, 5 pounds, okay? But it's not specifically referring to coffee A individually or coffee B individually. It's referring to the blend of the two, or the two mathematically summed together. So, whatever I have here for coffee A and whatever number goes here for coffee B, what this is telling me is that this number plus that number equals 5 total. Alright, and so this is typically how these problems work out. We are able to complete one of the two columns on the left, and keep in mind, according to the formula, number is multiplied, I'll put a star here, multiplied times the price, and that equals the third column value. And so we usually come up with the two columns that multiply. Now, as I said, the price numbers have completed the price column. We were given those numbers directly in the problem. So at this point, in order to complete the numbers column, we need to define a variable, and we'll just use x. Okay, we don't know how much of either one of these, the number of either coffee A or B, so I'll just pick one. It doesn't really matter which one you pick, but I will say that x equals number of pounds of coffee A. Okay, so since we've defined it that way, we could put x in here directly for the row of coffee A and the column of number. Now, if we can have at most, according to the blend, we can have at most 5 pounds, x of them have been used for coffee A, and so the remainder of the 5 pounds falls into coffee B. Mathematically, that would be written as 5 minus x. Now at this point we have our two columns completed. Okay, what we need to do from here is recognize the formula that relates the three columns together. Number is multiplied times price to calculate the value. And so the value for coffee A will be 540 times x. The value for coffee B will be 320 times 5 minus x, and it's important that you place the expression 5 minus x in parentheses. Alright, so from here, what we usually do is we take this third column that we've just calculated, and we go back to the problem and we look for some information that we haven't used. We've used the 5 in regards to the number column. The 320 and 540 were used in the price, and so the only number left is this number, which you don't want to just blindly use the only number that you haven't used yet. You still want to know what the problem refers to this number as. Well, it referred to this number as the total cost. Okay, and the total cost is the sum of the values of coffee A and B. So value, if you wanted to write it out in an equation, you could write this. It's not entirely necessary, but the value of coffee A plus the value of coffee B equals the value total. And a lot of the problems that we're going to work out this way. So what is the value of coffee A? It's 540x. We add that to the other expression. Value of coffee B, 320 times 5 minus x. These two values added together give us $19.30. So from here you can apply what you learned about solving equations and getting the x by itself from the previous chapters, and you can find the number of pounds of coffee A. And since you know x, you would also be able to use this expression to calculate the number of pounds of coffee B, and any other expression related to x in the table, and that includes the values. B reads, a web music store offers two versions of a popular song. The size of the standard version is 2.3 megabytes. The size of the high quality version is 4.2 megabytes. Yesterday, the high quality version was downloaded 3 times as often as the standard version. The total size downloaded, and again there's that word total that you want to pick up on, for the two versions was 4,321 megabytes. So how many downloads of the standard version were there? Okay, well, we were given the size of each version. Standard is 2.3 and high quality is 4.2. These numbers were referred to specifically for one version or the other. So standard is 2.3, we can put that directly into the table, and 4.2 was the size of the high quality version. And so we've completed one column, and now the second column, and again the number times the size in this case, which is more appropriate than the price, equals the total size. So each version individually is 2.3, standard version, and it depends on how many of those versions were sold, okay, or downloaded. So each one of these numbers would be 2.3, so number times size equals total value. Well, we weren't told anything about the numbers specifically to standard or just high quality. Okay, the only place where we were referred to the number was this phrase, 3 times as often. Okay, so the high quality version was downloaded 3 times as often as the standard version. So let's say standard version was downloaded 100 times. Well, high quality version was downloaded 3 times that, and so the high quality version would be 300. Okay, well, that's just one possibility. Another possibility is that the standard was downloaded 50 times. In that case, high quality would be 150. Alright, so we can't nail down these numbers without actually solving the problem in terms of a variable, but this does give us an idea as to how they're related. So if I know how many standard versions were downloaded, then I can calculate the high quality, and that should tip you off as to what the variable is supposed to represent. If we say x is the number of standard versions downloaded, then I could place X right here. And then from what we know by reading the problem, high quality is 3 times that, and to write 3 times X, we just place 3 beside the X. We have our 2 columns completed. To calculate the total size of each, we multiply number times size, giving us 2.3x for standard, and then 4.2 times 3x for high quality. And then our unused number, 4,321 megabytes. That is the total size of downloads. So we have the total size of each. If we add those together, we get the total size of all downloads. Mathematically, we would write 2.3x plus 4.2 times 3x equals 4,321. So this is our equation that we need to use to solve for x. And given x, we'll know all of the other information contained in the table. C reads 595 tickets were sold for a total sale of $13,844.05. Okay, and we're talking about Wild River Country, and so it's important to realize that this is the total number of tickets. This number here is the total value. Then they go on to tell us that the children's tickets are $19.99 each and the adult tickets are $29.99 each. How many of each type were sold last Tuesday? So we can already complete the price column. Adults is $29.99, children $19.99, and we have a similar situation to the previous problem. We were told the total tickets. So if I take my variable and I just pick adults or children, it doesn't matter which, but I'll say x equals the number of adult tickets sold, then I can place X directly into the number column for adults. And if 595 tickets total were sold, then I've used up X of them. And so the remainder, 595 minus X, would be placed into the children's row for the numbers column. We've got our 2 columns completed. Number is multiplied times the price, and that equals the value. So for adults we have $29.99x, and for children we have $19.99 times 595 minus x. Parentheses around the 595 minus x, very important, because we would want to multiply 19.99 times both minus x and 595. So at this point we look back to our problem and we recognize that the total value of all tickets is $13,844.05. The total value of adult and total value of children, if they're combined, they should equal this 13,000. So we write 29.99x plus 19.99, 595 minus x. These two added, the value of adults plus the value of children equals the total dollar amount for all ticket sales. Okay, uh, I'll go ahead and work this one out. We get just bring this down to the next line. What we really want to do in the first step is distribute the 1999 throughout the parentheses. So let's see, pull up my calculator. 1999 times, oh, I have a 5 in there, need to take that out, times 595, enter, and we get 11,894 and 5 cents. Okay. On the left we have two x terms, and if we combine those, 29.99 minus 19.99 would give us 10x. We can bring down our $11,000 figure to the next line. We have x on the left, and so we want to get rid of the 11,000 and the 10. 11,000 has to go first. We subtract it from each side. We're left with 10x on the left. And what do we have over here on the right? Let me just go ahead and use my calculator. 13,844 and 5 cents minus 11,894 and 5 cents. 1,950. And finally, if we divide both sides by 10, we would get x equals 195. So, well, what does x represent? The number of adult tickets sold. So, I could go back and fill in my table with the number 195 for adults. And children is the number of tickets for children was 595 minus the 195, the x that we just calculated. And so children's tickets would be 400. And always at the end of every problem, you do want to go back and reread the question. We were charged with finding the number of each type that were sold. We now know adults was 195 and children 400, so we've completed the problem. Okay, you're not always finished just simply because you found the number x. Sometimes you have to go back to the table and plug it into one of the expressions that you came up with to actually answer the question of the problem. Okay, so a different kind of problem, but if you'll notice, we still have the same form of formula. Okay, it's structured the same way. We're now talking about solutions, and what we have is base times percentage equals amount. Okay, so we'll apply that to a simple problem where we only have one solution. The question is, vanilla Dr. Pepper is 15% vanilla. How much vanilla is in 32 ounces of a vanilla Dr. Pepper? So vanilla is an ingredient in the vanilla Dr. Pepper. Okay, and that's usually the amount, okay? And the confusing thing about this formula sometimes is that the base and the amount have the same units. So in this case, we're talking about ounces, okay? It's obvious where the percentage goes. We have 15%, so that would be used in the place of percentage. But amount and base are going to have the same units of ounces. So you can't just look at the units and decide where it goes in the formula. Okay, the amount is going to be an ingredient. Not sure if I spelled that right, but it's going to be an ingredient in a solution. And so whenever you see the word solution, you should think the base. Okay, so what happened in this case? 32 ounces of vanilla Dr. Pepper. Well, vanilla and Dr. Pepper mixed together would be our solution. And so that goes, and we didn't have the word specifically as solution. Uh, in terms of solution, you probably should think of a mixture of ingredients. So 32 ounces was used in the place of the base. The percentage, 15%, was converted to a decimal. And when we multiply those two numbers together, we get the amount of vanilla, 4.8 ounces. Alright, so example 2, another straightforward application of the formula. There aren't two solutions. Okay, there's only one. So we don't need a table. We just need this formula. B times P equals A. So it reads, one fruit drink is made up of only 5% real fruit. Okay, so 5% is going to be our P variable, or it's going to replace the P. If we have 0.2 liters of real fruit, how much fruit drink do we have? So to make a fruit drink, apparently we're taking real fruit and we're mixing it with water and sugar and something else. So real fruit is an ingredient. Okay, and the ingredient is placed in the amount. Okay, percentage, 5% is changed to a decimal. And fruit drink is our base. Okay, it's the mixture of the real fruit and water and other things, and so you could think of it as our solution. So we have base times 0.05 equals 0.2. One step equation. To get the base by itself, we divide both sides by 0.05. Okay, and 0.05 cancels on the left, and so on the left side of the equal sign we have B by itself, and 0.2 divided by 0.05 gives us 4. Percentage is a unitless number, and so the base is simply going to inherit the units of the amount, which was liters. So we could write 4 liters. Example 3 reads, there is 1 cup of sugar and 25 cups of Kool-Aid. What percentage of the Kool-Aid is sugar? Here's our formula. B times P equals A. And we had one of our numbers hidden, sort of. 1 cup. Okay, it was written the word version. So 1 and 25. Well, where do we put our numbers? Well, 1 refers to sugar, which is an ingredient of Kool-Aid, and so 1 is going to go in the place of the amount, Kool-Aid is a mixture of water, Kool-Aid, and sugar. So 25 would take the place of our base, and we don't know the percentage. So we keep the variable p. To solve for p, we divide both sides by 25. "25 cancels on the left, and we are left with a p on the left side of the equation. And 1 divided by 25 is 0.04. This is the decimal form of the percentage. If we want to write the percent version, recall from chapter 16 that we have to move the decimal to the right 2 places, and then we can put our percent sign behind the number. So we can write 0.04 or 4%. Now, when the problem gets more complicated, when we have to apply that formula more than once because, say, there could be 2 solutions, then we are going to use a table as we're given here in example 4. So we have some salt solutions. We make a column for each variable in our formula: base, percentage, amount. It's important to recognize how the columns are related. Base is multiplied by percentage, and that equals amount. So we read the problem. Isaiah is mixing 2 salt solutions together. He is using 250 milliliters more of solution A than B, so we know how they're related, but we don't know the amount of each one individually. So we'll come back to that sentence later. And then in the next sentence, we're told solution A is 60%, solution B is 20%, and so we're given the numbers directly for the percentage column. And finally, if the resulting mixture has 170 milliliters of salt, salt is a specific ingredient in the salt solutions. So 170 is an amount. How much of solution A did he use? Okay, so our goal, our procedure, is to fill out the 2 columns that we multiply together. We will convert the percentages to the decimal form and then put those numbers in the table. So for solution A, we have 0.60, 60%. In solution B, we have 0.20 for 20%. Now, we go back to this tricky sentence here. He is using 250 milliliters more of solution A than B. Okay, so you may have to read that a few times and think about it, but what we're told here is we want to come up with a variable. And in this case, he's using 250 milliliters more of A than B. So this is tricky because what we're actually going to do to get solution A is add 250 to B. Whatever B is, we add 250 milliliters more to get the solution of A. So what we'll do is we'll write X is the base of solution B. So we replace the base, solution B, with X, and then we write for solution A, X plus 250. Okay, and if you want to use numbers to think about it instead of variables, which is sometimes helpful, if we have 100 milliliters of solution B, Then solution A would be 250 more, 350, which makes sense. We have more solution A than B, which is what this sentence obviously says. So we definitely need to add the 250 to whatever expression we have here for B. So we've filled out our two columns, base and percentage. Now we proceed in multiplying them together to get the amount. I'll just write 0.6 to shorten it up. So the amount would be x plus 250 times 0.6. And for solution B, we would write 0.2 times x for the amount of solution B. Notice that we didn't put 170 milliliters in either row. That's because it says we mix these two, solution A and solution B, we mix these two together. Okay, and this is how much salt we have in the end. Alright, so this, as in the previous problems, this gives us a total amount. And so the way we come up with our equation has always come from the third column that we calculated in our table, the amount in this case. And so if we add the amount of each solution separately, solution A plus the amount of solution B, we should get the total. So this amount, this represents, this expression here, 0.6 times x plus 250 equals the amount of salt in solution A. 0.2 times x represents the amount of salt in solution B. Okay, amount is a specific ingredient. In this case, it's the salt. We add the salt of A plus the salt of B, and we get a total of 170 milliliters of salt. Okay, this one wants us to solve this equation. So let's see here. We get rid of our parentheses first, and so we have 0.6x plus, okay, 60% of 100 is 60, and so 60% of 50 is 30, and so 60 plus 60 plus 30 would give us 150. I think that's correct. Let me check it with my calculator. I just want to make sure. 250 times 0.6. Enter. Yeah. Alright, 150. And then we have plus 0.2x equals 170. Combine the like terms. Here's an x term. There's an x term. 0.6 plus 0.2 would give us 0.8. And now we would subtract 150 from each side. And that would give us 0.8x equals 20. And now we divide both sides by 0.8. And we get x equals 20 divided by 0.8, enter, 25. X is represents the base of solution B, so in our table we could write 25 milliliters for solution B, and solution A is 250 more than that. So if we add 250 to 25, we get 275 milliliters. And this answers the question. Always refer back to the original question. It says how much of solution A did he use, and so we have to plug in our number or our variable in this expression for solution A. And so this is the number that we were looking for, 275. Alright, so here we're dealing with investment account or a savings account, percentages, principal. So principal is how much we put into the account, the percentage is our interest rate, and the profit is the interest that we're paid in the end. So we could label our columns. First two columns multiplied give us the third column, the profit. So we can write equals here. And then we have two funds, Fund A and Fund B. We're given the interest rates straightforward, 2% for Fund A, so 0.02, 6% for Fund B. And now we have to get clever and use our variable in a way that allows us to finish this principal column. And the only thing we're told about the principal is that he has $6,000 to invest in Fund A, which is different from the previous problems. We're just outright told how much he puts into Fund A, so we place the $6,000 here. And so the only thing we don't know is how much principal goes into Fund B. We have our two columns, okay? So if we multiply them together, we'll get the profit of each fund. And so we say 0.02 times 6,000 for Fund A, and then 0.06 times X for Fund B. Usually we add these two together and we set them equal to a total profit. Well, if you read back into this problem at the top, we weren't told a total profit. Okay, the only dollar amount we were given is $6,000, and the profit would be in terms of dollars. So the $6,000 was the amount of principal in Fund A. So what were we told? Okay, we were told in the question, how much did he invest in Fund B? That's going to be our X. It's the only thing we don't know. So we'll use our variable for the principal of Fund B. If both funds together, combined, added together, had a profit of 5%. So what we need to do is go down here and apply this principal times percentage equals profit formula to the total. Okay, well, what is the total principal? Well, if we add Fund A to Fund B, then we would come up with the expression 6,000 plus X, and then we're told the percentage that he earned, 5%. So if we take this total principal and multiply it by the overall percent profit of 5%, we get the total profit. So the key to this problem is realizing that there's two different ways to calculate the total profit. We could calculate it this way, or we could have calculated it by adding these two expressions together. So our equation just comes from the fact that we can calculate total profit two different ways. So on one hand, total profit equals this expression, and then on the other hand, total profit is 0.02 times 6,000 plus 0.06 times x. So these two expressions have to be equal. We take out the middle. There we are. Okay, 0.02 times 6,000 plus 0.06x equals 6,000 plus x times 0.05. And it's also important to notice that you have to be given this total overall percentage. You can't calculate 0.05 on your own. Okay, it's not acquired through the sum or the difference between these two percentages here. Alright, C. Two factory plants are making TV panels. Yesterday, plant A produced 2,000 panels. 5% of the panels from plant A and 2% of the panels from plant B. So here we are, percentages. Okay, this was given in the Word version. Okay, we could write that as 5%. How many panels did plant B produce? If the overall percentage of defective panels from the two plants was 3%. So here they go again. They've given us the overall percentage instead of the overall number, the total. Alright, so we have to be given this percentage. Okay, we can't get this any other way. So there's two factories, A and B. We have a total number produced. Well, hold on. We have, let's see, the number. Come up with an appropriate label for this column. We have the percent. And then we could say let's see, defective panels. Okay, so we'll call this defective panels. Alright, so we made a certain number, but some of them were defective. How many were defective from each plant? So defective panels in this last column. Alright, number times percent defective equals the number that are actually defective. So it said plant A produced 2,000 panels. That is the number of panels produced. 5% of the panels from A, so 0.05 for the A row, percent column, and 2% of B, okay, were defective. They didn't give us the number for B, so we'll say this is X, our unknown variable. If we were asked to define it, we would say X equals number of panels, good or bad, made at plant B. Alright, we have our two columns. We multiply them together. And now we run into the same situation as before in the previous problem. We need to know the total defective. Well, we can calculate that two different ways. We can add these two expressions together, which only completes one side of our equation, or we could say the total number of panels produced, 2,000 plus X, times the percent total, which this is the only other number that wasn't used, 3%, equals the total defective. So the key to this problem is that there's two different ways to calculate the same thing. So, in other words, we can take the sum of the two entries in the defective panel column, 0.05 times 2000 plus 0.02 times x, and set that equal to the other expression that should give us the same exact number, 2000 plus x times 0.03. And so the hard part is to complete the table, use your variable, define it appropriately, and set up your equation. I'll leave it to you to solve this equation. Okay, a new type of problem. Distance problems. Alright, we have a simple formula, same structure as the previous ones. We multiply two things together, specifically rate and time, and that gives us, that calculates the distance traveled. So let's get familiar with this formula. We have a simple problem here where Sam is driving down the road at 60 miles an hour for 4 hours. Could you use this information to find out how far Sam has traveled and how? Well, yes, we could. Okay, we can use our formula up at the top. Rate would be the 60. T would be the time, 4 hours. And it's also important to notice that the rate is based on hours, just as we were given the same units for time, hours and miles per hour. Alright, when these units are consistent, we can use them for rate and time in our distance formula. And so 60 times 4 would give us 240 miles. Distance is measured in miles. The rate is miles per hour, and the time is in hours. Okay. Example 5, if a car traveled 180 miles in 3 hours, find the speed of the car in miles per hour. So we have this formula, and as long as we have at least two of the numbers for either any two of the variables, then we can calculate the third missing one. So in example 5, we're given the distance already, 180 miles. So it replaces the D in the formula. And then we're given the time, T equals 3 hours. We want to find the speed, or in this case, the rate of speed, R. Well, in this case, we have to apply what we know about solving equations. We do the opposite operation with respect to the variable. And 3 is multiplying the R. To undo that, we divide by 3. 180 divided by 3 is 60, which is our rate. And 180 was in unit-wise miles, and 3 was hours. So the 60 has units of miles per hour. B, a jet flying 18.8 kilometers per minute has flown 84.6 kilometers. How long has the plane been flying? So in this case, we're missing the time. Same formula, D equals RT. We have our distance. Kilometers is another unit of distance. You've probably noticed on your speedometer. Or actually on your speedometer you have rate of speed, kilometers per hour. But kilometers is a distance, so 84.6 is going to replace the D. And we'll leave out our units so that we don't confuse them for a variable. And we are given a rate here. Whenever you see this per, you need to think of a rate. So kilometers per minute. 18.8 would replace R, and this is multiplied times T, our time. So what is our time? To solve for time, we divide both sides by 18.8. And so we have 84.6 divided by 18.8, enter, and we get 4.5. Well, what units? Is this hours, seconds, minutes? Well, if you look back at the problem, we mixed units of kilometers per minute with kilometers. So our units of time would be in minutes. So 4.5 minutes. Okay, and finally, just a simple application of the formula D equals RT. Construction crew has just built a new road. They built 7.68 kilometers of road in 6 weeks. At what rate did they build the road? Well, in this case, no one's really traveling. Okay, they're building this road, so they're doing a certain amount of work. But we could still use, just as distance is measured in kilometers, we could still replace the D with 7.68, the distance of road built. They have a rate of work, which we don't know. That's the question. At what rate did they build the road? And then we were told they did all this work in 6 weeks. And so 6 replaces T. To solve for R, we divide both sides by 6. R is by itself, so whatever we calculate on the left is our answer. And we have 7.68 divided by 6. And so another way of saying how fast they worked, instead of 7.68 miles in 6 weeks, we could say they built 1.28 miles per, with a fraction, week. So this was sort of their rate of work, or the speed at which they worked, instead of a speed at which they traveled. But the formula is still applicable. So here we are with our classic algebra problems, where we have either 2 modes of travel, or 2 people are traveling at the same time. And so to organize all the information that we're going to get, we're going to use a table, as we did in the previous problems. So let's start reading. Chloe can jog to school in 4/5 of an hour. When she rides her bike, it only takes 8/25 of an hour. If she rides 6 miles an hour faster than she jogs, and so it's not saying she jogs or she rides 6 miles an hour. It's telling us how those 2 speeds are related. They differ by 6. Okay, so for instance, her rate of jogging could be, let's say, 10. And so if she rides 6 miles an hour faster, then she would ride 16 miles an hour. On the other hand, she could jog 5 miles an hour. 10's a little fast. Maybe she jogs 5 miles an hour. Well, in that case, she would ride 6 more, and so she would ride 11 miles an hour. So with just that information alone, we can't really nail down the numbers. Okay, what we're going to do is the same as we've done in the previous problems. We apply a variable and we write expressions in the rate column. Now, we were given the times directly, so for jogging, we write 4/5 in the time column and 8/25 for riding. Now, this says she rides 6 miles an hour faster than she jogs. So if she jogs at a certain speed, we add 6 to that. Alright, so what we do is we say, well, if jogging is going to be our variable x, and so down here we write rate of speed for jogging. Then for riding, we can write the expression x plus 6. That completes our rate column. So at this point, to get the distance, as in the formulas above, we said rate times time equals distance. So 4/5 times x is the distance that she jogs, and then 8/25 times x plus 6 is the distance she rides. And so we've completed our table, and now we're going to try to figure out how these two distances are related in order to come up with our equation. Alright, this is where you have to really reread the problem and think about it. Okay, Chloe, in either case, whether she's jogging or she's riding her bike, what is she doing? Well, she's going to school. Okay, so if you assume naturally that she wakes up at the same house, her house, every day and goes to the same school, then she's going to take the same path. In other words, she's going to travel the same distance in each case. So distance jogging equals the distance of riding. Okay, and so there's no foolproof way of telling you how to come up with this format of the equation every single time. To be honest with you, it's going to come with a little bit of experience. So as I've said before, it's important that you pay attention to the problems that are worked in the workbook, but then turn around and try to get plenty of practice on your own working problems through Alex. Okay, and so in this case, we're not adding the two distances together. We're taking them and we're going to set them equal to each other. Like that. Okay. Alright, so how do I get, I've got 4/5 x. I'm going to have to erase this and then rewrite it so I can have space to work it out. Four-fifths x equals 8/25 times x plus 6. Alright, well, in this case we have an equation that has fractions in it. And so what we do is we take each side and multiply to get rid of the fractions. Okay, there's a 5 and then there's a 25. Lowest common denominator is 25. And so on the left side, the 25 cancels completely. And so now we have 8 times x plus 6. On the left side, 5 divides into 25 5 times, and so we would get 5 times 4x. If we get rid of our parentheses now, we could write 5 times 4 is 20x on the left, 8 times x is 8x on the right, and then we distribute the 8 to the 6 as well, 48. We have x terms on both sides of the equation, and so we're going to have to change the sign of one of them to combine them. Subtract 8 from both sides. We get 12x equals 48. And now if we divide by 12, both sides, we get x equals 4. And so it's not enough to just have this number 4 to sling around. You have to know what the 4 represents. And the way we use the variable up top, we used it in terms of the speed of jogging. So this is her jogging speed. Okay, and let's see, it gave us a rate 6 miles an hour, and so in this case this would be 4 miles per hour, the same units. Okay, in terms of time we were given hours. Alright, so this would be 4 miles an hour. How far away is Chloe's school? Well, we'd have to reuse one of the expressions from the distance column. You could use either one because we said the distances were equal. So I'll take 4/5 x. This is the distance of jogging specifically, but as I said, we solved this based on the fact that the two distances were equal. So I can use either expression. This looks like the simpler one. And we write 4/5, the time it takes her to jog to school, times the 4 miles an hour. 4 times 4 is 16 over 5. 5 goes into 16 3 times, and then we have 0.2 left over. And so the distance would be in miles, since our rate was in miles per hour, and we used a time in units of hours, 4/5 hours. The next problem, we have two trains leave a station at the same time, one heading north and the other heading south. The southbound train travels 70 miles an hour. The northbound train travels 90 miles an hour. How long? Okay, so we don't know the time. Will it take for the two trains to be 384 miles apart? Okay, our column headings are already labeled. We have a rate and a time for each train, and each train travels a different distance. So we'll say we have a north train to label our rows, and then we have a south train. Okay. And so they leave the same station. So if I use a star for our station, then you could imagine taking both of your hands, okay, a pencil in each hand, one on the left, one on the right for the trains, and you start drawing lines in opposite directions, and well, one's going north and one's going south. We'll just say north is to the right and south is to the left. If you took two pencils and you started at the star and you drew lines in opposite directions, and let's say you drew the train or the line with your left hand, um, you drew it slower. Then you drew the line to the right, which is faster, and you started drawing the lines at the same time and you stopped at the same time. Well, what would happen? This line would have a distance S. This line would have a distance of north, dn, and obviously since this one was faster, this distance would be longer than the distance south. However, the times that you spent drawing each line are equal. Okay, and that is a critical thing to know about these types of problems, because it didn't say anything about the time other than they left at the same time. Okay, and so imagine these two trains stopping, okay, traveling the same amount of time and stopping at the same time. Then what the problem is telling us is that they are 384 miles apart. So D south plus D north, even though one is longer than the other one, when we add the two together, we get 384. But it took each train the same amount of time traveling to accomplish this distance of 384 miles. Okay, this tells you how we're going to set up our equation in the end. Alright, 70 and 90 can be placed in the right column directly. The times are equal. So if one is x, the other one's going to be x. And for the distance, we multiply the rate times the time. And so distance for the north train would be 90 times x. Likewise, 70x for the south train. If we add the two distances, we get 384. Distance plus distance equals total distance apart. 70 plus 90, at this point you just go into equation solving mode, and so we'd say 160x, they're like terms, they both have an x, equals 384. To solve for x, we divide both sides by 160. So 384 divided by 160 equals 2.4. X equals 2.4, and we used x as a time, so this is hours. Okay, how long will it take the two trains to be 384 miles apart? 2.4 hours. We've answered the question. Okay, C, two trains leave the station 192 miles apart at the same time. Two trains leave station, so they're not leaving the same station anymore. They travel toward each other. One train travels 70 miles an hour while the other travels at 90 miles an hour. How long will it take the two trains to meet? Now we have two stations. Station 1 and Station 2. So if you imagine taking two pencils and drawing lines toward one another, one slower than the other one, okay, then the slower one would travel a certain distance, and then the other one would travel the remainder of the distance. You'd start drawing both lines towards one another at the same time, and we'll say this is the faster one and this is the slower one. But if you start at the same time, then at the time when they meet, they would have traveled each the same amount of time. It's just one is going slower than the other one, so it doesn't travel as far. But at some point, the two pencils would meet in the middle. Okay, well, how much distance total will they have traveled? Well, they would have traveled the 192 miles that the two stations have between them if they meet in the middle. Okay, so we calculate the two distances. One's going to be smaller than the other one, and the sum of the two should be equal to the total 192 miles. So, one train, and we'll say this one is slow and the other's fast. We have 70 and we have 90 miles an hour. Oh, and I put that in the time column. I should have put that in the rate. Sorry. We said that the times are equal. So if you define one as being equal to x, then the other has to be equal to x. And then rate times time equals distance. So for distance column, we get expressions of 70x and 90x. And if we add the two together, the distance of the slow train plus the distance of the fast train, then they will have to cover together all of the ground in between the two stations in order to meet. So in combination, 192 miles. Again, we get 160x equals 192. We divide by 160. We get x equals 1.2. Okay, how do we use x? Look back at your table. We used x in the time column, and so this would be 1.2 hours. And that does answer the question. Always look back at your problem and reread the question. How long will it take the two trains to meet? And we've done that. Check. 1.2 hours. And that completes chapter 17. Thanks for watching.